NanoHub U, online instruction.
Hey everyone, welcome to the last lecture of Unit 3. We're going to summarize and conclude what we've learned so far. So remember that we started off this unit on finite difference time domain by kind of explaining how the whole scheme works. And so, of course, we listed Maxwell's equations, but then we also added some extra terms. You see here, this JB and sigma BB. And of course, we said that these are not physical, of course, but these are going to allow us to actually, when we generate light in the time domain and then start to propagate outwards, to suppress reflections. So we can have systems that act like they're infinite or semi-infinite, even though, of course, in reality, we only have finite computational resources. So that's a very key trick. And then in order to get accurate integration of these systems, we use an approach which is actually borrowed from just ordinary differential equation solution method called the leapfrog method. But then we're doing this on a so-called E lattice, and the E lattice allows us to have more accurate computation than we could otherwise in 1D, 2D, or 3D. And so then in order to actually use this method, of course, we could try to directly write down the equations and then write a solver, but luckily that work's been done for you, and there are several solvers out there, and the one we focused on the most is called MEEP. And so MEEP is available for download through this website, or you can actually run it as a tool without any installation of software and only using a free account on NanoHub using this link, nanohub.org/tools/meep. And so this allows you to do very powerful finite difference time domain solutions, and it has a lot of special features. We said we can do arbitrary dimensionality and boundary conditions, which by itself is very significant. We can do perfectly matched layers, which I had mentioned earlier. Do subpixel averaging, which gives us greater accuracy than we would have otherwise. We can do symmetry, which can reduce the size of our cells and also speed up our calculations. And it's fully programmable because we have actually three interfaces. We have both the graphical user interface, and then we have the scheme interface, as well as the C++ interface. So we can use whichever approach we want, and so it's tremendously flexible overall. So just to briefly recap, like, what is the value of this subpixel averaging? So what we said is that using a leapfrog method, we should have scaling of the error as a function of the resolution to go as like 1 over resolution squared. But in practice, some methods actually only scale like 1 over the resolution in terms of their error. And so that's actually a big problem, because that means we have to use a lot more computational resources than should be necessary. And that all comes from basically the way that we are defining dielectric when you have curved surfaces. So you basically have this so-called stair-stepping effect. In order to get rid of the stair-stepping, then we use this subpixel averaging, which is motivated by the physical content of Maxwell's equations. And then that allows us to recover this 1 over resolution squared behavior, which you can see here. And this was originally proposed about a decade ago. And then we showed that this kind of approach can be applied to a broad range of problems. This is just one of many examples that we covered in this unit, where we have silver nanoparticles used in photovoltaic light trapping. And you can see that basically they enhance the field by orders of magnitude compared to control without the silver nanoparticle. And this is the front texture that you can see up here, kind of like the top-down view. And you can see that the overall absorption curve looks like this. And you can also quantify what is the parasitic loss. And it is non-trivial, but it's small enough so that you can potentially get relatively high short circuit currents in silicon thin films, which are almost comparable to what you'd get in, say, multicrystalline wafer silicon, but of course using much less material. And then we also discussed another potential application, which is to increase light trapping in perovskite silicon tandem cells. So this is going one step beyond just the single single crystalline silicon, but actually including 2 different material layers. And of course, the rationale for that is to get even higher efficiency and higher performance. And so here, actually, we have both thin film crystalline silicon and perovskite integrated into a single structure. And then we can actually directly capture what kind of absorption is happening, and then what parasitic losses, including the spiromytad, some reflection, and then a couple other loss mechanisms, which are relatively small, like the indium tin oxide. And then that actually gives us a very clear indication of the potential efficiency, perhaps could be up to 25 to 28% for these tandem cells, which is pretty significant. And so in conclusion, we found that finite difference time domain has a tremendous amount of flexibility and applies to a very broad range of problems. In the next unit, we'll explore some multi-physics challenges as well as some finite element methods to help solve them.